On Daytime on 2 now, statistics investigated in today's maths topics.
This program has been designed mainly for recorded use. Full details are in the notes for teachers. In the 1930s, coal mining was at the center of the country's industry. And today, coal mining is still vitally important. However, coal mining is also dangerous. Underground accidents, some of them fatal, will always be part of a coal miner's life. But despite the danger, we still pay men to go down the mine. Why is coal production so important to the country? Well, take the figures for the last 30 years. These figures are accurate enough, but to see what's happened, use a bar chart. Clearly, production has fallen. If you compare 1947 with 1978, you can see a big drop. But coal's importance lies in the way we use it. Power stations, iron and steel manufacture, domestic use, industry. In power stations, the amount of coal used went up, not down. Coal is increasingly important for the generation of electricity. In 1947, it was 14% of the total produced. In 1978, it was 66%. But proportions are easier to see as pie charts. The angles show the proportions in each case. For power stations in 1947, the angle is 14% of 360 degrees. That's just over 50 degrees. In 1978, it's 66%. That's nearly 238 degrees. The area of each circle is in proportion to the total amount of coal produced. 196.8 million tons compared with 119 million tons. The area of a circle is in proportion to the square of its radius. So if you're drawing your own pie charts, you'll need to calculate the radius by taking the square root. As oil gets scarcer and more expensive, and controversy still surrounds the use of nuclear power, so coal is likely to be even more important as a fuel for our power stations. The forecast for the year 2000 looks like this. How does this compare with other countries, like the USA and Japan? Here are the pie charts for 1947 and 1978. Of the three countries, only the United States has increased its total coal production over the last 30 years. Will this trend continue? Here are the forecasts for the year 2000. In all three countries, a greater output is expected, mostly used as a fuel to generate electricity in power stations. It's predicted that coal will remain a very important source of energy until well into the 21st century. The facts and the predictions are clear once you use a diagram. Our survey of world coal production figures missed out a country you may not have heard of before, Outer Statistica. The coal mining industry of Outer Statistica is very run down. This worries the people in charge of the coal production. Could they make the figures look better than they really are? No problem for outer Statistica's unscrupulous coal barons. They concentrated on the last 4 years. Well, there's nothing actually wrong with this graph, but it would look better spaced out. A clear upward trend here. So why not show the trend as a line graph? Again, there's nothing wrong, but the increase doesn't look very impressive, at least not yet. That's better. Now, provided we show exactly what we're doing, there's nothing actually wrong with this graph. It may not tell the whole truth, but it does show what happened. Of course, if you really want to deceive the public, how different from the true picture. But the unscrupulous outer statistician coal barons are even more cunning. Using piles of coal to represent the output, they decided to draw pictograms. They looked at the last 4 years' growth and assumed it would continue at the same rate. These lines show the correct proportions of coal. But now see what the coal barons did.
Coal, a proud record. The facts speak for themselves.
Do they? The picture shows volumes of coal, and these volumes are not in the correct proportions. We should be comparing the heights, a very different picture, even if we were certain about future trends. After all, we started from this graph. This is an egg packing station. About 10 farms send their eggs here. The packing station handles over 200,000 eggs every day. The eggs are graded by machine according to their weight, from grade 1, the biggest, to grade 7, the smallest. As you might expect, there are more eggs of some grades than others. With this particular batch, there seem to be more of the larger grades than the smaller. To see what was happening, we let the trays build up for a few minutes. A more accurate record is kept by these counters on the back of the machine. By tradition, the counting is done in dozens. But before we look at the figures, we have to look more closely at the limits of the various grades. Most eggs weigh between 45 and 70 grams. The European regulations state that grade 1 is for eggs weighing over 70 grams. Grade 2 eggs weigh 65 to 70 grams. Grade 3 are 60 to 65, and so on. Grade 7 eggs weigh less than 45 grams. But you may have already realized that this definition won't do as it stands. What about an egg which weighs 65 grams? Is it grade 2 or grade 3? In fact, the correct definition of grade 3 is eggs weighing 60 to 64.9 grams. And for grade 2, it's 65 to 69.9 grams. So this 65-gram egg should be in grade 2. Because the machine weighs to only the nearest tenth of a gram, all eggs can be graded. So now we know the exact definition of the egg grades, let's have a look at the data for these eggs. We can represent this data as a histogram. The weights and the number of eggs in each interval. Then draw in the columns, one for each interval of weights. In this batch, there were no eggs in grade 7, so no column. In grade 6, just 5 dozen eggs. The column hardly shows. In grade 5, 89 dozen. Grade 4, grade 3, grade 2, grade 1. But is that right? Grade 1 eggs are 70 grams or over, so why should the column only go to 75 grams? The answer is that we don't know. The machine makes no distinction between weights over 70 grams. It might be that about a third of these eggs were between 75 and 80 grams. Or perhaps a few are over 80 grams. If you don't have the data in the first place, you just have to use common sense. The point to remember is that the area is what represents the number of eggs. And of course, all the best graphs have a title. Accidents on motorways are not uncommon. Many of the accidents are thought to be caused by bunching, drivers getting too close to the car in front. The highway code recommends leaving a gap of at least 1 yard for every 1 mile per hour, and that means a minimum gap of about 2 seconds. But do drivers leave a sufficient gap? The Road Research Laboratory decided to find out the facts. The study of over 7,000 vehicles produced a list of gap sizes. We grouped together the gaps in different ranges to produce a frequency table. Each interval is in effect half a second. If we take the first interval and start to draw a histogram, the first column will be here. Another way of labeling the horizontal axis is to use the midpoint of each interval. In this case, 0.25. The next column will have its midpoint at 0.75, and so on. This is the histogram produced. The general pattern is clear. Out of the 7,000 vehicles observed, over 2,300 were following the vehicle in front with a gap time of 2 seconds or less. That's 32% of the vehicles, many of them traveling at high speed. Indeed, 16% of the vehicles were following with a gap of less than 1 second. But in the table we used, some of the data is already hidden. The number of cars were in fact recorded separately for the outside and inside lanes. If we now separate the histogram in the same way, we see 2 different patterns. For the inside lane, most of the groups contain roughly the same number of vehicles. But for outside lanes, more vehicles were following with smaller time gaps. As a comparison, the Road Research Laboratory decided to look at the time gaps on a busy non-motorway road. This time, we've got the percentage of cars in the different intervals. 12.4% were following it under 0.7 seconds. 10.8% were between 0.7 and 1 second. 9.3% between 1 and 1.3, and 6.6% between 1.3 and 1.6 seconds. But this isn't a true histogram, unless we reduce the height of the left-hand column to compensate for its having a larger class interval. The areas now show the correct percentages, but we've also had to relabel the vertical axis to allow for this. This accounts for 39% of all the cars observed. It suggests a background distribution something like this, with the rest of the motorists safely off to the right. But 39% is too high a proportion of motorists tending to drive too close to the car in front. Accidents could happen. So the Road Research Laboratory decided to see if they could do something about this. They installed a sign, but not just an ordinary sign. Down the road is an infrared beam which measures the gap between the cars. This information is transmitted to the sign, and if the gap is too small, the sign lights up. So, does the sign make a difference? Here's the histogram of the gaps before the sign was put up. And here's the histogram of gaps after the sign was put up. The histograms indicate there is an improvement. The gaps tend to be a little larger than before. Not much, but they are larger. So the sign does work. Mind you, some drivers never learn. Today, we can buy many things from vending machines. But what actually happens when you put your coins in the slot? As buyers, we expect the machine to accept our coins and give us the product we've paid for. The machine owner, however, wants to protect himself from being cheated by people who try to use counterfeit coins. So the coin mechanism must be able to distinguish between real coins and counterfeits. Inside this machine is one of the most sophisticated coin mechanisms available today. The first thing the machine does is to make sure the coin is metallic. Then, if it is, it releases the coin down an inclined plane. In this position, the coin passes through a strong magnetic field, and because the coins are metallic, the magnetic field slows them down. The time taken for the coin to pass through the mechanism is measured by the photoelectric cells at the end of the slope. The mechanism accepts or rejects coins depending on their time. To set the limits of acceptance or rejection, the manufacturer has to know the times for the various coins. With over 2,000 million coins in circulation in this country alone, the data on timings is obtained from a sample. Working with a small sample of coins, we tested the time each took to pass through the mechanism and noted the results. Counterfeits of the same size as real coins are fairly easy to obtain. But what happens when we measure the time they take to go through the mechanism? Each unit of time on the clock was about 1/7,000th of a second. 200 units is about 3/100th of a second. The times for the counterfeit coins were all between 185 and 260 units. But for the real coins, they were all between 265 and 315 units. In this case, there's no overlap. So we can set a limit at about 263 units to accept all coins and reject all counterfeits. These two samples might have come from background distributions like these, but it seems unlikely that there would be enough overlap to worry about. So next time you use a vending machine, remember it recognizes your coin as